strategy was, right? We defined what it means for a function to be continuous at a point, right? Established some 3 criteria, and really the third one implies the first 2. That's the one you got to know. Remember, we said that for a function to be continuous at a point, at that point, the limit of the function has to equal the value of the function, right? And if we extend that idea to all the points on an open interval, then that's how we define continuity on an interval between points, right? If the function is continuous at each of the points on the interval, then it works for the whole interval. And then we went one step further with that, and we said, okay, well, we could even include the endpoints if we invoke the idea of one-sided limits, right? If we say that, okay, so we have continuity on the open interval from A to B. To include the endpoints, we extend that definition where the value of the function at the left endpoint, for example, so f of A would have to equal the limit of the function from the right as x approaches A, right? And the value of the function at B, so f of B would have to equal the limit of the function from the left as x approaches B, okay? All right. And then we defined some classifications or categories for discontinuities, right? We said essentially there's 2 big categories, removable and non-removable. What does it mean to be removable?
You can just simplify it.
Good. You can move or add one point, right? It's easy to repair the function by just reassigning one individual point. Non-removable can't be done. You'd have to, with that, you'd have to completely scrap the function because there's an infinite number of points to move, right? And then some additional language we called, I think in our book, or in the online book, they're going to call this maybe a point discontinuity, okay, because it's just a single point. They're going to call something like this, where it's a finite jump, they're going to call it a jump discontinuity, where there's a break in the function. And then if there's an asymptote, it's an infinite discontinuity. Okay. Not that that stuff is that big a deal, but just so when you see that language in the Math Excel assignment, you know what they're talking about. Okay, so we looked at a couple problems like this. You're going to see some like this where they've got a function and you have to determine where is the function. Is it discontinuous? If so, where is it discontinuous? And maybe what type of discontinuity is it, right? Let's do another one of those. How about if I give you something like, there's one I want to definitely throw at you. How about this one? This one here. Okay, think about that one, please. Any suggestions about that? Is it discontinuous anywhere? See some heads shaking. Okay. We want to defend why it's maybe not discontinuous, why it is continuous. Go ahead. Okay, good. So the bottom is positive valued everywhere, isn't it? Right? X squared plus 1 is a positive valued function. It's never 0 and it's never negative, right? And that's a good way to think about it. We'll come back to this in the future. The way I kind of like to talk about this is you always want to look at the behavior of a function and think about the 2 rules that we have to follow for real numbers. Can't divide by 0, can't take an even root of a negative number, right? So where's the danger zone here? Well, we have an expression with a variable in it that's in the denominator. So think about the red bubble, right? You don't even have to, this isn't super complex, but later on they might get harder. So the red bubble, whatever it is, just can't equal 0, right? So what's that look like in terms of algebra? Well, it just looks like x squared plus 1 cannot equal 0. A not equal to sign acts just like an equal sign. We can do algebra the same way, right? So if we were to solve for x, we would find that x squared cannot equal -1, but there's no danger in that, right? Okay, what if, let's try a different one. What if we had something like this? What if we have, let's see, I'm going to do, let's do cosine first. Yeah, that'd be good. So let's do f of x equals x over cosine x. What do you think about the trig limits? That one doesn't quite fit. Okay, but what's going on with that one? Is that one discontinuous anywhere? Where? Okay, so in terms of a bubble, we don't really have any, there's no even roots here to worry about, right? But we do have a function of x on the bottom, right? So that's the part that we've got to be concerned about. So whatever's in the bubble cannot equal 0, right? Okay? So green bubble cannot equal 0. What's in the green bubble? Cosine x. Okay, so then we just need to find all the places where cosine x equals 0, and those have to be excluded, right? So what are those?
Pi over 2.
Okay, so we get pi over 2 or negative pi over 2, or, and we can look on the unit circle, can't we, and see all those. Those are going to be the places where on the unit circle? Top and the bottom. Okay. What's the problem with this? You're giving me correct answers. Evan, what do you think?
Goes around forever.
Goes around forever. There's an infinite number of them, right? So we got to figure out a way to say that. This is a good question. You'll see this in the future. You have an idea?
Pi over 2 plus n pi.
Okay, something like that. Good. Right. We want to be able to say all of those values. Now, what are those? If we make a list, what you started to do, that would be something like pi halves, 3 halves pi, right? Negative pi halves, etc., right? Odd multiples of pi, right? So couldn't I just write that whole list as those are going to be all the places where I have an odd number times pi over 2? Does that make sense? Right? So how can we define an odd number in terms of a convenient set? We don't really have, I mean, I guess you could say let J be the set of odd numbers and then these are going to be all the elements, but there's an easier way to do it. What do you think? How can we do it maybe define in terms of a more common set, like the set of integers? Let's say that n is the set of integers. Or so in other words, n is an element of the set of integers. So n is an integer. Okay. I think a lot of times we use j for some integers. So if n is an integer, how can we do that? How do we say an odd number in terms of an integer? How can I say an even number? If n is any integer, how do I create an even number? Put 2 in front of it, multiply it by 2, right? That works, doesn't it? Think about it. Any integer times 2 is guaranteed to be even, isn't it? Right? Okay, so then what could I do to make it odd? What about it? Well, if I put 1 in front of it, it's going to work half the time. Because then, it would work for 1, but it wouldn't work for 2. But if I know, now think about this, if I can guarantee that I can get myself to an even integer, where's the next odd integer? Plus 1, right? So couldn't I say 2n plus 1, and that guarantees I'm going to have an odd integer, right? Everybody see that? Okay, so then I could say, I could take this expression, and I could write this as, oops, where'd I go? I could write this as the quantity 2n plus 1, or minus 1, doesn't matter, right? I just have to step 1 away from that even integer on the number line, times pi over 2, right? Does that make sense? And so, if I wanted to find all the places where this is discontinuous, then we could say something like x is not equal to 2n plus 1 times pi over 2, like that. Right? Those are all the places where I get a 0 on the bottom. Okay? What are those going to look like? Another question. Are those going to be point discontinuities or infinite discontinuities? This is something, and we'll talk about this in different contexts in the future. Think about what happens if I try to take a limit at those places, right? If I want to know, the function is undefined there, right? We just said x can't equal those values, right? If I try to take a limit of this function, f of x, to see where the ant is approaching, right? As x approaches any of those, right? Let's just say 2n plus 1 pi over 2. What happens? What happens when I try to evaluate directly? What do I get? Plug stuff in. What do I get on the top? Don't give me a specific value, but I get, on the top I get a number, right? Whatever value of n I'm dealing with, right? So I'm going to get something like a number divided by 0, right? So what's that look like? What did we say that always looks like for a limit? We'll talk more about it here like within the next week, but we kind of dealt with this a little bit. We said in terms of a limit, we're done. It's no limit, right? Next week we'll explore that further, but I think I mentioned that it's always going to end up being infinite, isn't it? Right? It's going to be a vertical asymptote every time, right, that happens. And we'll talk more about that in the future. You talked about that, I'm assuming you talked about that in Algebra 2 and pre-calculus. If you have a rational function, for example, and you have a 0 of the bottom but not the top, isn't that always a vertical asymptote? Right? Remember that? Is that what you're going to say?
You answered the question.
Oh, okay, I got you. So then this is an infinite discontinuity, right? If you get something like that happening. Make sense? Okay. Yes or no? That make sense?
Yeah.
Kind of. So if you were to take a limit and you get a number divided by 0 that we previously called no limit, that means it's infinite. It's a vertical asymptote for sure every time. Okay. What kind of vertical asymptote? Next week we'll figure out what the behavior is around that asymptote. Because if I say something like, I have a vertical asymptote at, let's say, a positive 3, if that's all I know, well, there's a lot of things that could happen, right? The function on the left could either go up or go down. The function on the right could also either go up or down. So there's all different types of things that could happen. Next week we'll have some tools to figure out which one it is. But we always know that no limit means vertical asymptote like that. Okay? Number divided by 0. All right. So this would be another example, wouldn't it? Right here. Right? If we took a limit of this guy as x approached 3, we'd get 1 over 0, right? So we know that's a vertical asymptote, and so it's non-removable. Right? Looks like that. Okay. How about, let's try another one. go to this guy. This is where we left off, okay? So we want to find A to make this continuous, right, to repair this function. We just left off at the end. What was our thinking on this? In order for it to be continuous at x equals 2, right, because that's where these two pieces knit together, what has to be true again? What are the conditions for continuity at a point? Okay, the limit, well, yeah, the limit of the function has to equal the value of the function, right? And so f of 2 has to equal the limit of f of x as x approaches 2, right? That's our condition. Well, where is the function defined at 2? That's in the top one, right? So up here, when x equals 2, that's the behavior of the function. So therefore, we can say f of 2 equals 2 cubed, which is 8, right? We good with that? Okay. So the ant actually steps on the point. He's on this part of the function. He actually steps on the point 2, 8, right? Okay, so then when we approach from the other side down here, whoops, when we're walking from the right, from values of x greater than 2, the ant has to anticipate stepping on that y value, right? So that leads us to this expression down here, or this equation. The limit of f of x as x approaches 2 from the right, because then the ant is walking on this piece of the function, ax squared, has to equal 8, right? And so we can use that information to set the value of a to make it 8, right? And that's kind of where we got stuck, where we left off. So what's that look like? If I take this limit, if I evaluate directly, what do I get? If I'm approaching 2 from the right, what value am I approaching? 2, right? I'm approaching from the right, but I'm still approaching 2, just like I was before. So when I evaluate this limit directly, it works the same as it did a week ago, right? I'm just going to plug 2 in for x squared. This part right here, the limit of ax squared as x approaches 2 from the right, is just 4a, right? Okay? Well, that has to equal 8 because that's the value of the function. So what does a equal? 2. Yeah, right? If I solve for a has to equal 2 in order to make those functions come together. Okay? Questions on that? Make sense? All right. A couple other things I wanted to just throw at you. And this is kind of review stuff. A lot of this early stuff is. What does this mean? What function is this? A lot of times you'll see it as int x or maybe something like that. You know what that is? Remember that from probably last year? Greatest integer function? Never did that. Okay, well, let's talk about that. Okay, greatest integer function. A lot of times it's written that way. Here's what that means. A greatest integer function is defined as the least integer that is greater than or equal to the input value. Hang on a second. Greatest integer function. No, hang on a second. I say it again. It's equal to, here's the graph, then we'll figure out how to say it. So it's going to look like this. It's going to look like, the words get confusing, but the picture's not at all. The greatest integer that's less than or equal to the input value. That's how we say it. So for example, what would be int of 3.1. What's the greatest integer that's less than or equal to 3.1? 3, right?
We did do this.
So you did do this, okay, all right. Figured you probably did. So then it's just gonna look like this, isn't it? So that's 1, 2, 3, so it'd be 3, right? What's the greatest integer of 0.1? 0, good. What's the greatest integer of negative 1.7? Negative 2. Okay, you see what we're doing with that? Okay, this is similar to, there's another function in math that's similar to this that we call a ceiling function. A ceiling function is always going to give you the least integer that's greater than or equal to a number, right? Here's a great way to visualize this. Think about it as, here's what the greatest integer function does. If you take an infinite string and you're going to put knots in the string at every integer, any bead that's on that string, you're going to push it to the left until it hits it, until it gets caught on a knot, right? That's what the greatest integer function does. It's the same thing as a floor function, right? Does that make sense? It's going to push it down until you're at a knot. If I start at 3.1, well, I'm going to push it until I hit that knot at 3, right? If I start at negative 1.7, I'm going to push it to the left until I get to negative 2, right? Does that make sense? It's a good way to kind of internalize what that does. A ceiling function does the opposite. It pushes it to the left. So if we said, and that's not in our book, but you'll see it in the future. I want you to see this. So if we had something like f of x equals ceiling of x, then it's like it's pushing it up or to the right. So what would the ceiling of 1.7 be? 2, right? We're going to push it to the right from 1.7 up to 2. Okay, make sense? So if we look at a greatest integer function, where is it discontinuous, obviously? At the, well, more than just whole numbers, at the, well, how do we say that? 'Cause whole numbers would just be integers, right? Positive or negative whole numbers, right, would be integers. So at all of the integers, it would be discontinuous. Sometimes we call this a step function also. Okay? This is useful to us in many ways because, like, if you look at things like physics, for example, a lot of times, you guys all took chemistry, you know that the energy levels of an electron in an atom are quantified, right? Well, they jump from level to level instantaneously, right? See what I'm saying? So that matches like quantum behavior. Or in a digital circuit, you have TTL voltages where it's either, you know, you don't have these continuous voltages. You've got voltages where it's either true or false, right? And so you try to emulate something like this with the you know, the voltages inside a computer circuit, an integrated chip or something, right? So, make sense? I mean, there are applications of it, but this is what the math looks like. Okay. How about, so you're going to get a couple questions that relate to that. And you'll be fine with them, but I just want you to know what they're talking about when they say integer function. Okay, how about this one? Here's another terminology that pops up that you already know. Okay, when people talk in math about an extended function, they're talking about a function that's been repaired, okay, a discontinuity that's been repaired. So, for example, if we say something like f of x equals x squared minus 4 over x minus 2. Okay. Discuss the, in the words of the textbook, discuss the continuity of that function. Could you tell me about the continuity of that function? Okay, so there's going to be, where, first of all, where would it be discontinuous?
2.
At 2, right? Because we can't divide by 0, right? So we can see immediately there's a bubble in the bottom, and the bubble equals 0 when x is 2, right? Okay, what's the behavior there? Now we gotta go back and see, this is kind of cool because we're taking a new concept, but we're integrating it with stuff we already learned how to do a few weeks ago. What are we gonna do to figure out what the behavior is? What are we gonna do? It's gonna be a more work kind because we're gonna take a limit, aren't we? We're gonna see what happens as the ant approaches from either side. In this case, back here, where was it? Right here, for example, when the ant approached 3 from either side, the limit blew up, right? I got a number divided by, when we approached 3, I got 1 divided by 0, which we know is a vertical asymptote, so it's no limit, right? Same thing happened, didn't we have one down here? Yeah, with the trig function, x over cosine x, right? At all of the odd integers or the odd multiples of pi halves, we got a number divided by 0, and so those were all vertical asymptotes, right? So those were all non-removable discontinuities, okay? What about this guy? Okay, if I take a limit of this function as x approaches 2 is 0 over 0. That's more work. Now, what does that correspond to if you think back to kind of pre-calculus, maybe a little bit of honors algebra 2 stuff when you talked about rational functions? What happened when you got a value of x that was a simultaneous 0 at the top and the bottom? It wasn't a vertical asymptote. What was it? It's indeterminate form. What is that? What have these all been when we've looked at these kind? Remember, what have we called the? What do we call that? It's a point discontinuity, and we used to call it a hole, didn't we? Right? What's the more work that we do here? Remember, this means more work.
Filling in the hole.
We filled in the hole, didn't we? Right? We created a new function that agrees with this one every place except at that one point. We filled in the hole, meaning we repaired the discontinuity, didn't we? Right? This is equal to the limit. If I factor the top and cancel the factors, what am I going to get? X plus 2. Good. I'm going to get the limit of x plus 2 as x approaches, that's supposed to be an arrow, x approaches 2, which is 4, right? Our trick, remember, was to trade this function with a hole for this function with no hole, right? So if we want to repair the extended function, what's the point that we have to add, right? Well, the function is not defined at, we would call this probably g of x, right? If we want to repair f of x, x is not defined at 2. We would have to define a value for 2. We're going to write like a piecewise function, right? What's the value that we'd have to add? 4, right? See what I'm saying? Okay. F of x is undefined at 2, but if we define the value f of 2 equals 4, we repair the function. So in your assignment, for example, it might say, write the extended function for f of x. Well, there it is. It's just x plus 2, isn't it? Right? That's the one that fills in the hole. Okay. F of x, remember, looks like f of x looks like this. Let's see what f of x looks like. X plus 2, it starts there. So it goes like this. Right? It's got a hole. But g of x, if we call that g of x fills in that hole. Right? So g of x would be this function with the hole filled in, so that's the extended function, the repaired function. Okay? Questions on that? You've already done all that work, haven't you? What else? Okay, last thing I'll show you. And I'll let you guys work tomorrow on this stuff. Is an existence theorem. An existence theorem in math, all they are, they don't really, the way they help us is they prove that something exists, but then we still have to go find it, right? So it says, like, if this is true, then there exists something else, right? And so we know at least that it's going to be there when we look for it. So here's our existence theorem. You guys fill in the blanks for me. What if I have if the function f is continuous on the closed interval from a to b, and k is any number between f of a and f of b. I'm going to write it this way, such that, well, I'm just going to say between. So we don't know which is bigger, so we'll do that. Any number between, and between this is a concept you understand. F of A and f of b. What do you think you could tell me? Let's draw a picture. What do you think you could tell me about the relationship between the continuous function and this value k? So let's graph a little picture here. Let's say that this is A and that's B. The function is continuous, right? So we're going to start, let's say, here. And we'll just draw a random function that ends up maybe like right there. What do you think?
K is always defined.
It's always defined, true. Okay. This is what we'd call f of A, right? And this is f of b, right? If k is some number that's between f of a and f of b, what do you think you could tell me about this function? Now keep in mind it's continuous, which means I'm going to place my pen on the board at the point a, f of a, and draw without picking my pen off the board until I get to the point b, f of b. If k is some number between, somewhere, any number between f of a and f of b, call that k. What do you think's always going to happen? Say it again. Well, okay. You guys are getting more complicated than you need to be here, maybe. So,
It's going to be in between points A and B on the x-axis.
what about it?
It's going to be in some.
When you say it, what do you mean?
The where it crosses the
Okay.
line.
Okay. So in other words, the function would have to have the value k somewhere between a and b, right? Does that make sense? Another way of saying that is the function has to intersect the line y equals k somewhere between its endpoints. If k is between f of a and f of b, there's no way to avoid it, is there? I can't draw a function without picking my pen off the board that crosses that line. It may cross it more than once, right? But it has to cross it, doesn't it? So it just tells us that there's going to be a value that we could look for and find. That's the value of an existence theorem. Okay? So if we finish this thing off, it just says between f of a and f of b, then, so it's an if-then statement, all right? It's a conditional statement. Then there exists, they say there is, but usually we'd say there exists, right? It's an existence theorem, at least one number c on that closed interval from a to b such that f of c equals k, right? So where's C on my picture? Yeah, it's going to be about right there in this case. See what I'm saying? There has to be one place like that. Okay? So we got 8 minutes, is that right? Okay, I never can remember. So let's try one of these then. What's a math problem where this would come into play? How about something like this? Okay, let's say f of x equals x squared plus x minus 1. And let's take the interval where x is greater than or equal to 0 and less than or equal to 5. We're going to define f of c. We're going to assume the existence of some value, some number c between a and b. And let's say that f of c equals 11. We want to verify that the intermediate value theorem applies. So does it apply? And if so, what's c equal to? Okay? So let's go kind of couch this in the language of the intermediate value theorem. So our function, here's our function, right? X squared plus x minus 1. We know, first of all, let's verify that it works. Is this function f of x continuous on our interval? It is. There's no bubbles to worry about, right? Meaning there's no place where x's are on the bottom, there's no even roots. There's no place where we could have a big pickup here, right? It's defined everywhere. And one thing that we're going to say about polynomials that maybe you've already talked about, I can't remember last year if you would have or not, but polynomials are everywhere continuous. They're well behaved, right? They're well behaved because not only are they continuous, we're also going to show that they're differentiable later, right? So they're really well behaved functions. And that actually is the mathematical description of a function that is continuous and differentiable. Okay? But the differentiable part means nothing to you right now. It will later, but the continuous part does, right? Okay, we can draw any polynomial without picking our pen off the board on any interval. Okay? So check. We met that condition. It's continuous. One other thing has to be true, though. K has to be a number between f of a and f of b. Well, what's k down here? 11, yeah, right? K is the same thing as f of c, isn't it? Right? We said up here, why isn't this working? Come on. There we go. So k was where our function crossed through this, this horizontal line, and we said that where that happens is at x equals c. So by definition, then, isn't k just equal to f of c, right? So let's see, does that fit our criteria? Is f of c between f of a and f of b? Well, what are a and b in this case? 0 and 5, right? Here's our interval, right? So what is f of a, in our case, is f of 0. What's that equal to? -1. Good. Okay. F of b equals f of 5. What's that equal to? 29. So is f of c between f of a and f of b? It is, right? F of c is 11. So therefore, we know that there exists at least one place where our function has a value of 11, right? Does that make sense? Because k equals 11 and that's in between. Now all we have to do is go find it algebraically, which we would do how? How do I find where our function has a value of 11? Well, I could graph it, but let's not graph it. Set it equal to 11 and solve, right? Probably by factoring, right? So we're going to set f of x equal to 11, right? So x squared plus x minus 1 equals k, which is 11. And by solving that, we're finding c, right? We're finding the value or values of c where it occurs. So that's just some Algebra 2 stuff, right? How would we solve this? Oh, put it standard form, right? Set it equal to 0. So we get x squared plus x minus 12 equals 0. That factors easily, right? What are my magic numbers? Good, plus 4 minus 3. What are my solutions then?
-4.
4. So the other part of this says, find the value of C guaranteed by this theorem. So are my solutions -4, 3? Are those the values guaranteed? -4 is not. How come?
Because of the,
It's not on our interval, right? So even though, yes, the function equals 11 at -4, that's not the answer we're looking for. We're looking for the values guaranteed by the intermediate value theorem, right? And that, the only one guaranteed is 3. That's the only one that ends up being between our endpoints. Right? It wants to know, we know because this satisfies the conditions of the intermediate value theorem, there has to be at least one place where the function has a value of 11 between 0 and 5. Has to be at least one. Well, what did we find? We only found there is only one at 3. Okay, but that's the only one we're looking for in this case. I see some quizzical looks out there. Ask a question. What do you think?
So our graphs, when we're graphing it though, would it be like 3 and then
Yeah, so let's graph it. Let's graph it. Here's our function, right? If I graph this thing, let's just pull up Desmos and graph this. So the function is, so I can see it, I'm going to write it over here. So it's x squared, what did we say, plus x minus 1. Plus x minus 1. Okay, everybody agree that's our function? And we want to know, when does that function have a y value of 11? So I could just graph the function y equals 11. Whoops, y equals 11. And I'm just going to find where they cross. Well, one place they cross is right there. See what I'm saying? At the point 311 we found. Right?
So we find the x value by putting it
Right, by just... Right, but first we had to show that there existed that place, right? Because we were looking at this function between x equals 0, which was -1, and clear up here at about there, right? That one. See what I'm saying? So on that interval, it only crossed that line one time, and that's where it was.
Okay, and then since there's bracket, it's like closed.
Right, it's closed.
It's never gone above 20, or it's never gone.
Well, so that's just it, because it's a closed interval, that's just, the importance of that is that we can put our pen on the board, right? We can put our pen on the board at A and take it off the board at B. And because we met the criteria, we were guaranteed to have gone through the y value k, which was 11 in our case, at least once. It happened at x equals 3. So that was the value of C we were looking for. There might have been more than one. What if, when we solved that thing, we ended up getting 2 solutions that were both between 0 and 5? Then there would have been 2 values of C. See what I'm saying?
Yeah.
Okay. We cover a lot of stuff in here, don't we?